Look up at the night sky. What do you see? A sea of stars, scattered like diamonds on black velvet. For centuries, we believed they were fixed points of light, eternal and unchanging. We mapped their courses, predicted their movements, and thought we understood the grand celestial dance. But what if we were wrong? What if something else, something vast and unseen, is pulling the strings? Imagine a force so powerful it can reach across billions of light years, a cosmic puppeteer whose stage is the entire universe. This is a story about a mystery that begins in the quiet, empty spaces between the stars, a subtle whisper that suggests everything we know might just be the opening act of a much larger drama. This invisible influence is not a gentle nudge. It's a relentless directional pull. Picture a leaf caught in a gentle breeze, drifting aimlessly. Now, imagine that same leaf caught in a powerful current, swept along a determined path. This is what astronomers believe they have found. Entire clusters of galaxies, each containing trillions of stars, are not drifting randomly as the expansion of the universe would suggest. Instead, they are moving together in lockstep toward a single specific point in the cosmos. Imagine you are on a raft in the middle of the ocean. All around you, the water seems calm, but slowly, you realize you are moving. You are not paddling. The wind is still. You look around and see other rafts, distant islands, all moving in the same direction as you. You are caught in a current, a vast invisible river flowing through the ocean. This is precisely what astronomers observed when they looked out into the cosmos. They saw not just one galaxy, but entire clusters of galaxies, immense families of stars, all caught in a single, powerful cosmic current flowing together toward a mysterious destination. These are not small structures. We are talking about galaxy clusters, the largest gravitationally bound objects in the universe. Each one is a sprawling metropolis of hundreds or even thousands of galaxies like our own Milky Way. Yet that is not what the data showed. Across a vast expanse of space, spanning billions of light years, these clusters were all streaming in the same direction, toward the constellations Centaurus and Hydra. It was a coordinated movement on a scale never before imagined. This cosmic river, the dark flow, moves at a breathtaking speed. These galactic superstructures are hurtling through space at more than 2 million miles per hour. This velocity is not explained by the gravitational pull of any known object or collection of objects within our observable universe. Scientists have mapped the distribution of matter, galaxies, gas, and dark matter as far as our telescopes can see. They have calculated the gravitational forces at play, and yet none of it adds up. To understand a river, you must find its source. For the dark flow, that source is hidden. So scientists had to look for its effects, for the ripples it leaves in its wake. Their search took them back in time, all the way to the dawn of the universe. They turned their attention to the oldest light in existence, a faint, pervasive glow that fills all of space. This is the cosmic microwave background, or CMB. It is the afterglow of the Big Bang, a snapshot of the universe when it was just a baby, a mere 380,000 years old. The CMB is remarkably uniform, a testament to a time when the universe was an almost perfectly smooth, hot soup of particles and energy. But it is not perfectly smooth. Imprinted upon it are tiny temperature fluctuations, minute variations that represent the seeds of all future structures. These ripples, just one part in 100,000, are the ancestors of a star, a galaxy, and even the great clusters of galaxies we see today. By studying these faint patterns, we can learn about the universe's history, its composition, and its ultimate geometry. The key to unlocking the secret of the dark flow was a variation of this cosmic trick. It's called the kinematic Sunyaev-Zeldovich, or KSZ effect. While the standard effect tells us about the presence of hot gas in a galaxy cluster, the kinematic version tells us if that cluster is moving. Imagine the CMB as a steady, uniform rain falling straight down. If a car drives through the rain, the front windshield gets hit by more raindrops per second than the back windshield. In the same way, if a galaxy cluster is moving through the sea of CMB photons, the photons will appear slightly hotter in the direction of motion and slightly colder in the direction opposite its motion. This temperature shift is incredibly small, measured in microkelvins or millionths of a degree. Detecting it is one of the most difficult measurements in all of observational cosmology. It's like trying to detect the warmth of a single candle from 1,000 miles away. To do this, astronomers, led by Alexander Kashlinsky at NASA's Goddard Space Flight Center, used data from the Wilkinson Microwave Anisotropy Probe, or WMAP. They identified the locations of hundreds of massive galaxy clusters and then stacked the CMB data from those locations, averaging them together to amplify the incredibly faint signal of their motion. The results were stunning. When they analyzed the data, they found a clear, statistically significant signal. The clusters were not stationary, nor were they moving randomly. A huge swath of them, stretching out to a distance of over 2 billion light-years, showed a coherent bulk flow, the dark flow. It was as if an invisible cosmic wind was blowing through the universe, pushing these galactic behemoths along a specific axis. This discovery, however, was not without controversy. The measurement is extraordinarily difficult, and other studies using different methods and data, particularly from the more recent Planck satellite, have failed to find such a strong signal, or have found results consistent with standard cosmological models. The scientific community remains divided. If the dark flow is real, it presents us with a profound cosmic puzzle. Where is this river of galaxies flowing? The direction is clear. It points toward a patch of sky between the constellations of Centaurus and Hydra. But when we point our most powerful telescopes in that direction, we see nothing special. There is no supermassive congregation of galaxies, no great attractor on a scale large enough to explain the immense pull. The source of this motion, the thing that is dragging a significant fraction of the observable universe along with it, appears to be completely absent from the cosmic map. In our standard model of cosmology, gravity is the only force that can act over such vast distances, and gravity is caused by mass. Therefore, there must be a gigantic concentration of mass in that direction, pulling the galaxy clusters toward it. The frightening and exhilarating possibility is that the source of the pull lies outside the boundaries of what we can see. Our vision of the cosmos is limited. Because light travels at a finite speed, we can only see out to a certain distance, an edge known as the cosmic light horizon. This boundary is about 46.5 billion light-years away in every direction. We cannot see what lies beyond this edge because the light from any object more distant has not had enough time in the 13.8 billion-year history of the universe to reach us. Our universe might be infinite, but our view of it is finite. What the dark flow suggests is that our observable universe is not a closed system. It is being influenced by something from the outside. It's as if we are on a small, well-lit island, and we see footprints leading out of the light and into the all-encompassing darkness. We can see the tracks, but we cannot see the creature that made them. The edge of the observable universe is not a physical wall. It is a horizon of information. Beyond it, the universe almost certainly continues, perhaps forever. It is simply the part of the cosmos that is, for now, invisible to us. The theory of cosmic inflation, which is our best explanation for the early universe, suggests that the universe expanded at an exponential rate in the first fraction of a second after the Big Bang. This means the true size of the universe is vastly larger than the portion we can see. Our observable bubble is just one tiny patch in an unimaginably vast and possibly infinite cosmic quilt. If this is true, then it's entirely possible that just beyond our horizon, there exist structures of unimaginable size and mass. These could be titanic superclusters of galaxies, or vast filaments of dark matter, far larger than anything we have ever witnessed. These pre-inflationary structures, remnants from a time before our universe inflated, would be so massive that their gravitational pull could be felt from across the cosmic horizon. They would be tugging on the matter within our visible sphere, pulling it toward them and creating the phenomenon we call the dark flow. The dark flow, in this scenario, becomes a form of cosmic weather, a breeze created by the gravitational topography of the larger, unseen universe. Our local galaxies are simply flowing downhill toward a massive gravitational valley that happens to lie just over our horizon. What kind of structure would be massive enough to exert such a powerful pull across billions of light years? The candidates are truly mind-boggling, titans of the cosmos that would dwarf anything within our observable sphere. Imagine a concentration of matter, not of 1,000 or even 10,000 galaxies, but of millions. a structure so dense and so vast that its gravitational well extends across the horizon, a cosmic drain pulling everything toward it. Such an object would have to have formed in the very early universe, before the period of inflation that stretched the cosmos to its current immense size. These are what some physicists call pre-inflationary structures. Before inflation smoothed everything out, the universe may have been incredibly lumpy and chaotic. While inflation would have flattened most of these lumps, it's possible that some truly gargantuan ones survived, stretched out to astronomical proportions. If one such structure happened to end up just outside our cosmic horizon after inflation, its gravitational influence would persist. It would be a ghost from the universe's past, haunting our present-day cosmos with its relentless gravitational pull, orchestrating the strange coordinated dance of the dark flow. This theory forces us to reconsider the very nature of our cosmic address. We tend to think of our universe as being, on the largest scales, homogeneous and isotropic, the same in every direction. This is the cosmological principle, a fundamental assumption of modern cosmology. But the dark flow, if caused by a nearby superstructure, would violate that principle. It would mean that there is a preferred direction in the universe, a special axis pointing toward this unseen mass. Our cosmic neighborhood would not be average. It would be located on the slope of a massive cosmic mountain or valley. There is another, even more exotic possibility, one that takes us beyond the realm of massive structures and into a landscape of pure speculation. What if the pull is not coming from something in our universe at all? What if it's coming from something outside of it? Some theories, rooted in string theory and M-theory, propose the existence of a multiverse, an infinite ensemble of parallel universes, each with its own physical laws, floating like bubbles in a higher dimensional space. Our universe would be just one bubble among countless others. In this breathtaking scenario, the dark flow could be the gravitational influence of another nearby universe. Imagine two bubbles floating close to each other in this cosmic foam. The mass and energy in the neighboring universe could exert a gravitational pull on our own, a pull that would be felt across the dimensional void that separates them. This pull would not be directed toward a specific object within our universe, but rather toward a specific direction in the higher dimensional space where our universe resides. It would be a gentle but persistent tug from a cosmic neighbor. This would manifest in our universe as a bulk flow, a coordinated movement of matter toward the point of closest approach. The galaxy clusters we see would be like iron filings aligning to a magnet held just outside their container. We can't see the magnet, but we can see its effect on the filings. The dark flow, then, could be the first observational evidence that we are not alone in the multiverse. It would be the cosmic equivalent of hearing a knock on the wall from the apartment next door. A sign that another reality exists, tantalizingly close yet forever beyond our reach. Today, on August 11th, 2025, the mystery of the dark flow remains unsolved. It stands as one of the great cosmic enigmas of our time, a persistent anomaly that challenges the foundations of our understanding. Is it a real signal, a whisper from beyond the veil? Or is it a phantom, a ghost in our data born from the immense difficulty of measuring the universe on its grandest scales? Telescopes like the Euclid Space Telescope and future CMB observatories are gathering more precise data, hoping to settle the debate once and for all. If the dark flow is confirmed, it will open up a new chapter in human exploration. It will tell us that our universe is not an island, but is connected to a larger reality we are only just beginning to perceive. The source could be a titan from the dawn of time, a pre-inflationary relic of immense mass. Or it could be the even more fantastic possibility of a neighboring universe in the multiverse. Either answer would fundamentally change our place in the cosmos. We would no longer be observers of a self-contained system, but participants in a much grander, interconnected cosmic drama. But what if future observations show nothing? What if the dark flow fades away under greater scrutiny, revealed as a statistical error? Even then, the story will have been worth it. The quest to understand it has pushed our technology and our theories to their absolute limits. It has forced us to confront the boundaries of our knowledge and to ask daring questions about the nature of reality. It is in grappling with mysteries like this that we truly explore the universe, not just with telescopes, but with our minds and our imagination. The search itself is a journey of discovery, And so we are left staring into the darkness at the edge of everything we know. The great river of galaxies may or may not be flowing toward an unseen shore, but the possibility has been planted in our minds. We look out at the vast, silent cosmos, and we can't help but feel a sense of profound wonder and a touch of suspense. We have pulled back a corner of the celestial map only to find that it may not be the whole map at all. We are left with the ultimate question, the one that has driven us since we first looked up at the stars. What lies beyond?